Hello, everyone, and welcome to Module 4 of the Introduction to Data Science webinar series, sponsored by Population Data BC and the Canadian Urban Environmental Health Research Consortium. I'm glad you could make it today. We've got Aman Verma on the line. We'll hand it over to Aman. Thanks a lot.
Okay, hi guys. I hope you can all hear me well. Welcome to the fourth module of this this Introduction to Data Science Machine Learning, called Advanced Unsupervised Learning. Unsupervised learning might be a little more unfamiliar to many scientists, which I think is too bad because I think it can be very beneficial for our work. And so I think what we're going to be doing in the session on Thursday is we'll be looking at some canoe data on local climate zones. And so what I'm going to do now is to use that as an example to give you a sense of what unsupervised learning is all about. Okay, so local climate zones, for those who aren't, or those of you who aren't familiar with them, are basically the Earth is divided into a number of regions, and then on those regions, some of those properties are measured. So they have the mean building height and the sky view factor. Here are some different variables that you can measure on these regions of the Earth. What people have done is that they have classified each of those regions of the Earth into one of 15 categories. And so here I'm giving an example of some of the properties they use to define the local climate zones. And then for one particular type of climate zones, there's, I think, 15 or 16 of them, give you the sort of definition of what it means to be a compact high-rise. So for this one local climate zone compact high-rises, it has a sky view factor of between 0.2 and 0.4 and a canyon aspect ratio of greater than 2. The meanings of these properties don't matter, but my point here is that this is, although they didn't use unsupervised learning to create these categories, that's something they could have done. So what unsupervised learning is about is taking variables like this on the regions of the Earth and then making your own categories out of them. So the computer would automatically generate take these properties and say, well, they basically belong into 15 basic categories. And you can see that because this pattern occurs very often, where this sky view factor is in combination with this canyon aspect ratio is seen. And so how it all works is through correlation. So if you take a look at all of the local climate zones, and then take a look at how their rough properties are described, it's clear that these were not found by a machine, that they were found by humans because the numbers are round. But it gives you a sense that they're a little bit loose. If you had some some region whose properties are basically like this, but maybe one of them is really far out, then they would be roughly belong into this category. So no categorization is perfect. It can still help you understand your data, and that's what makes unsupervised learning a little bit harder to describe as opposed to supervised learning, because you don't have this really hard concrete target that you have in supervised learning. So what is unsupervised learning? It's, if you've heard of it, clustering data. You don't have any predictors or predicted thing. You just have a bunch of variables, and you want to put them together. So that doesn't sound really helpful, it's a little bit difficult to understand why it's useful. So I'm going to introduce three different techniques for unsupervised learning: k-means, hierarchical models, and a very light overview of principal components analysis. And I'll give you a little example in each of how it's used in scientific analyses. So the general idea is, why do you want to do this clustering? Why do you want to do unsupervised learning? It's basically because we want to summarize our data. The idea here is that you want to discover structure in your data rather than predicting some outcome. And the reasons why you want a cluster is pretty similar to why you want to visualize data. Like when nobody is going to say that a dot plot of your scientific data is going to lead you to to reject some hypothesis, and it's not always clear what the purpose of that plot is before you do it, but everyone does it. You have to, and it's quite obvious with visualization why that's such an effective way of summarizing your data. Humans are really good at looking at things visually and seeing patterns in them. And that's the same kind of reason why you would want to do clustering. Sometimes it can help you summarize data that is very complicated. And when data becomes a lot bigger, these tools become a lot more important. So if we have, say, 300 variables, we might be able to just eyeball it, going through an Excel spreadsheet and taking a look and saying, well, there's basically 3 types of data here. But when it becomes 300,000, that it becomes totally untenable. So I think these tools are really useful, and I think they are, again, underutilized by scientists, or perhaps just underreported in the literature. Okay, I'm gonna start with the k-means algorithm, which is really a simple but powerful tool, I think, in the clustering toolbox, and sort of the basis for most unsupervised learning. And I'm going to also talk about the expectation maximization algorithm, which is used, special cases used to fit the k-means algorithm. Okay, so what is k-means? You basically want to find the mean of k clusters. So if given a data set like this, notably these are just 2 x variables. So you can imagine in this little data set with 40 points in it that this is the local climate zones, but with 2 dimensions here. So maybe like a canyon aspect ratio on one hand and a sky view factor, I think was the other one called, on the horizontal axis. But anyways, it's important to note that the vertical axis here is not some predicted thing. These are just we're just trying to group data points together. So here we show this data set, and when you just take a look at it, you eyeball it, and you want to say, well, if I were to make 2 groups out of this data, I would probably pick something like this. I would say the ones on the left seem to group together pretty well, and the ones on the group on the right seem to cluster together pretty well as well. And what does that mean? That means there's a lot of variables that seem to have similarly high on this axis, but a little bit low on this axis data. So they might not be exactly the same, but they're pretty close together. So it's all about correlation here. So when you pick k equals 3, or when you pick 3, you might choose another set of these clusters. What k-means as an algorithm is having the computer automatically find, or having the statistical algorithm automatically find these cluster means for you. Why do they call it specifically k-means? It's actually just a weird historical precedent. I think in one of the textbooks, Mackay points out that it's as if Newton called differential calculus the calculus of calculating the variable x. It's really weird to include the variable name inside there. K is obviously arbitrary, but it doesn't have any specific meaning beyond that. So that's the purpose of the k-means algorithm, is to discover these little clusters. So how do you find clusters like this in data? You use a specific case of the expectation maximization algorithm. And that sounds really fancy, and I'm going to go through this in a little bit of detail, because it's a really kind of amazing algorithm, and it helps you understand how k-means works and where it might fail. Okay, so the idea is you have to actually pick the number of clusters before you start this algorithm. So you have to set k to equal something before you start. So you set k to equal 2, or you set k to equal 3. You randomly pick those means, And when you initialize, you start off your algorithm with random cluster means. So just to go back to the previous slide, here, if this was my cluster, my mean would be something like this, like the centroid of this little oval, right? So that you're picking random points at the start. The way the algorithm proceeds is first it assigns each data point to its closest mean. So if you have two cluster means of k equals 2, then each data point gets assigned to one or the other mean. And then for each data point set, meaning for each set of data points assigned to each of the means, you move the mean to its center. Now that sounds a little bit complicated and like it's kind of circular, and it's because it is circular, but you repeat until the assignment doesn't change. In the next slide, I'll show you a visual example of it that makes it quite clear. But I did want to mention that this is a specific case of the expectation maximization algorithm as developed in a classic 1977 paper by Dempster, Laird, and Rubin. So they themselves pointed out that this method had been proposed many, many times by earlier authors in a variety of different literature, including gene counting and other industrial applications. But it's something that that comes up over and over again. The discovery that this algorithm is actually a special case of EM. Anyways, its introduction into statistics was a major advance, and it has numerous applications, even in supervised learning and in unsupervised learning. Something you'll still see today in modern machine learning papers. Okay, so now to go for a sort of a visual example of what it means to do k-means. So say you started with the same data set that I was showing earlier. That data set is actually from the Information Theory, Inference, and Learning Algorithms text by Mackay, which is available for free for on-screen viewing. And I really recommend Chapter 20 for an introduction to what k-means is all about, but also what clustering and unsupervised learning is all about in a variety of different problems. I find him an extremely engaging writer, and also has very nicely designed assignments, so not assignments, but I would say exercises for the reader that really makes you think and allows you to understand the algorithms really well. Okay, so let's say you start off with 40 points here, and you pick your k to equal 2. So you want to find k equals 2, or 2 clusters within these data. So you start by randomly assigning 2 different points in your data. And so you're just picking random points on your in your space. And as we'll see later, this makes a difference. It's not always going to go to this same place if you pick different points. But then after you pick your k-means, your 2 means, then you assign each of the data points to its closest mean. So we can see that for this mean in the top left here, the data points, there's only a few of them that really are closest to that one. And so they get assigned the sort of plus sign, and the rest of them get assigned the diamond over here. Okay, so now the update step. So we take all the little plus signs over here, and we move the mean to their center. So what does that mean in this case? It means that like we take the mean of their horizontal axis and the mean of their vertical axis, and we put their mean there. Basically in the centroid. I don't think it's precisely the centroid but anyways, it's the mean of their variables. And we do the same thing for the other mean. So that doesn't move it too much because it was taking up most of the data points. So, and here's the trick. You iterate between those 2, assignment and update, and you'll see how it slowly moves the means around. So the next step, it says, okay, now let's assign all of the points again. And so we have all of these points on the left-hand side get assigned to this mean, because now they're all of a sudden closer. And on this one, it's going to make a big change, because now this point is nowhere near the mean of the diamonds. And when you update again, you see that this mean gets pushed over to the center of the diamond ring, and you update once more, and you see that there's only this one diamond gets changed. So it seems like less and less data points are getting changed, and that's indeed how you tell when to stop the algorithm, is when things stop changing. That is, when you try to, you make the update, and there's no, and you do the assignment again, and there's no changes to which get assigned to which mean. And that's, it's kind of it's a beautiful algorithm. It works really well in many different situations. It's also used in statistics for things like multiple imputation. It's used in Markov models. But I wanted to show, and in this particular example, the assignment is the expectation part of expectation maximization, and the update is the maximization. So I thought it would be interesting just to show you an example how the algorithm works. So if you start the k-means in different points, it's going to have a different effect on what clusters you end up with. So in this example, also out of Mackay, he takes the same data set, but does 2 different runs with k equals 4. So now you've started off with 4 different means, and you're trying to make 4 clusters out of them. On the first run, you kind of get, he assigns randomly assigns the means over here. You kind of get what you would probably, a human would pick if they were trying to pick out 4 different clusters in this data set. You know, 1 in each sort of quadrant of the data. That's how the human eye would probably separate it as well. But on run 2, if you start the means in different places, it actually doesn't end up with the same solution. It's not a totally implausible solution. It's true that this cluster does seem to be pretty different than this sort of side, but you can see how it's not entirely, you're not going to, it's not deterministic at all. It's stochastic. And so you have to watch for and really maybe try k-means a couple of different times if you're getting really different results. And it can be very sensitive to outliers, which is something that Mackay talks about in detail. So one other question that comes up with k-means is how many clusters do you choose for this method? So how, and unlike supervised learning, like when we're learning about hyperparameters for supervised learning, we could do things like, let's just try different values for, say, lambda in regularization, and we'll measure the cross-validated accuracy, and whichever's more accurate, we'll use that one. We actually don't care what the values are. But with k-means, it's a little bit more difficult because the accuracy metric, the thing that we're using to say whether a cluster is good, isn't as clear, because the purpose of our clustering was to help us find some sort of structure in our data, and that's something that's quite hard to measure. So the only way to really target how many clusters we should have is by come up with some measure on how good the clusters are. And the way to do that is say, okay, we have a set of points here, and we would call this one probably a good cluster, and then maybe this one a worse cluster compared to this one. And you can just imagine this is on a 2-dimensional plane, I guess, which it is, but that this one is it's more spread apart than this cluster. So that's what makes it a worse cluster. How do you measure how spread apart a cluster is? Well, you measure all of the possible distances between the points. So if I took every possible pair of points, measured the distance here, and then squared it, you could take the absolute value, but traditionally it's a square, I would get the within group sum of squares. So that's the way that we tell how tight our clusters are, and it's that tightness that we use to try to understand how many clusters we should use when we're running k-means on our data. The visualization that people use for this is called the spree plot, and so you can see here this isn't the same set of data at all, but they tried with a varying number of clusters. So they tried k-means with k equals 2 to k equals 14. And then for each of them, they measured the within-group sum of squares. So obviously, going from one cluster, which is like obviously not really a clustering algorithm, you're just really measuring the within-group sum of squares for the entire data set. It's going to be a big drop to 2 because you're drastically reducing your within-group sum of squares just by putting in 2. But as you increase the number of clusters, it might not be as clear how much value you're going to get out of that. And it's not something that's going to always decrease. You can actually have, especially when you get to the very high number of clusters, going from 14 to 15 might actually slightly increase your group sum of squares. It's got this weird name called a scree plot because it actually is a scree. I think I was reading as a collection of rock fragments at the base of the cliff. It comes from the shape of this sort of the base of a cliff. And so this kind of shape always comes out in the scree plot because there's a huge drop from 1 to 2. And what you're really looking for is sort of that elbow where you're saying, well, here at 3 clusters, I really got a little bit of value left to going to 4, but not so much after I continued. So that's sort of how you would tell the difference, sort of get a sense of how much value you're getting out of increasing your k in k-means. Okay, so one thing that I kind of glossed over is how you measure the distance between points. So since in every part of the EM algorithm, we have to measure the distance from the mean each of our k-means to each of our points to get an idea of like which one's closest, we have to have some measure of what that means. So what does it mean for one to be closer to the other? The most obvious measure, especially in 2 dimensions, is the Euclidean distance, so which is effectively equivalent of just measuring the straight line distance, taking a ruler and measuring the distance between the 2 dots. But as the number of dimensions increases, so like even in local climate zones where you might have like 12 variables, that's still, the Euclidean distance doesn't behave intuitively. And I think that behavior, that disconnect between our intuition about how Euclidean distance works on 2 dimensions and how that breaks down when you expand it to several, to very high dimensional data is described quite well in the elements of statistical learning in chapter 2. There's a very interesting problem given but it's relatively hard, but it makes it quite clear that our intuition is not always what should guide us, especially when we're using 2 dimensions as our basis. And so there are different distance measures that are used in practice. One of them is called the Manhattan distance. So this one sums the distance along each dimension. So the Euclidean distance is pretty obvious. Say this is 2 dimensions, you just draw the straight line distance between the 2. But with the Manhattan distance, you're actually taking the distance along each dimension, and you're saying like, okay, this is the x1 dimension because this is the horizontal dimension, and saying, okay, this is the difference along this dimension, this is the distance along this dimension, I'm just going to sum them all up. Now, it looks a little weird, and that name is also kind of funny. The reason why it has that name is because Manhattan, I think this is true at least, it has a grid-like structure, or at least whoever came up with the name thought it had a grid-like structure. And so if you're trying to get from any point in Manhattan from one place to the other, you have to follow that grid-like structure, so you have to move along these lines rather than take the straight line distance. But in continuous data, it's less clear why you would use this, but in binary variables, it becomes much more obvious how this is more intuitive. So say you have, unlike the local climate zone data, you have some binary variables, maybe 5 or 6. And so they're represented as 0, 1, 1. And you're trying to measure the difference between, say, a person who has 0, 1, 1 and 1, 1, 1. And so there's only one variable that's this different there. The Manhattan distance would say the difference between those two people is exactly 1, because we're summing the distance along each dimension. But for the Euclidean distance, it's going to try to measure the straight line distance across, and so you're going to end up with, the square root of that difference. I think in that case it'll actually also be 1, but if you had more differences, it'll be different. It'll give you some less intuitive numbers, and so it does make a difference on how things how things play out in terms of the algorithm. So, but I think that Manhattan distance would be more relevant for binary data. The Chebyshev distance is a little bit strange. It's the difference along the most different dimension. So here, this is a little bit of a different data set where the distance along this dimension is not as much as this one. You only take this line. So you only take the most different dimension. That seems strange, but I think what it helped me understand is when you take a look at the what's called the Minkowski distance. The Minkowski distance puts all of these three things together. So it shows that the Euclidean distance and Manhattan distance and the Chebyshev distance are all special cases of the Minkowski difference. And so this formula is not as complicated as it makes it out to be on Wikipedia, where I got this from, because the Euclidean distance is really just Pythagorean theorem. In a squared plus b squared equals c squared, you can see there's a squared, and then there's a square root over there when p equals 2. But what the idea is that as you increase the p in the Minkowski distance, as you're going from the Manhattan distance to the Euclidean distance, you start to get closer and closer to the Chebyshev distance. So you're favoring the most different dimension a little bit. So that's what the Euclidean distance actually does, is it favors the most different dimension a little bit more than the Manhattan distance, whereas the Manhattan distance says it doesn't really matter which one is different, they're all equally weighted. So that just gives you a little bit of a sense. I like to sit down and play with the numbers to really get a sense of how these Euclidean distance and Manhattan distance will work in my data. But I just like to give you at least the terms so that you can play around with it if you're interested. Okay, so now time for an example, and I think this is kind of a cool example. I had a student a few weeks ago come to me with this, and I said, hey, k-means might be a useful way to solve this problem or get you a better handle on your data, and that's really sort of the story of unsupervised learning, is that when somebody has a very large set of data and they just don't know how to pull it apart, they haven't been able to come up with a visualization that really helps them understand what are the general characteristics of their data, what are the patterns, unsupervised learning works really well. Okay, so just a short bit about the problem that he was trying to solve. So soda consumption is considered now to be an important public health problem. Soda consumption, like the consumption of all highly sweetened beverages, is associated with many diseases like diabetes and hypertension. So what we're trying to do is study customers at a large grocery store retailer in Quebec and look at their shopping habits. So what he had extracted from this data is all of the proportion of each of what you spent, how much of it was on soda, and do that every month for 2 years. So for every customer for 2 years, he had calculated the proportion they spent on soda. And when he plotted that, so for each person, he had a little time series of 24 points. It was completely impossible to understand because it just went all over the place, and he couldn't get a sense of the different kinds of people that were in his data. So again, why did I recommend this to him is because it helps him summarize the data and pick out individual trends. So I'm just going to show you how he did this. So he chose 16 means, and so in his analysis, each variable was one of the months of data. So he had 24 dimensions, 24 variables, which each one was how much did each customer buy in terms of soda. And when he plotted, and then he did the k-means clustering, and then he plotted within each k-means cluster, so this is everybody who belonged to cluster 1, this is everybody who belonged to cluster 2, and he plotted them all on top of each other. Now, what's great about this is that you can see that there are big patterns in the data. And so there are a lot of people who are doing very, very similar things. One interesting thing that came out, I think it was a good example over here in cluster 11, there is a group of people who pretty much only buy soda during December, during the holiday season. And then for the rest of the time, they don't buy any soda at all. And I think that a lot of people, when they hear that, they're like, well, that's obvious. I have some experience with that in my life, and I have a hypothesis already about why that's happening. And it doesn't matter what that hypothesis is. What matters is that you immediately came up with it, and that you could see that. Like if you plotted all of these people on top of each other, it's going to be very difficult to come up with that immediately. You're just not going to see that there is a group of people like that. But hopefully I'm trying to give you a sense that it's this visualization later that matters. Like, is there a group of people that is behaving similar to what you would expect or a little bit different? And does that allow you to generate hypotheses that are going to be useful in future work? So yeah, so this is k-means in the soda time series example. Okay, so I'm going to move now to hierarchical clusters. Hierarchical clustering is an interesting sort of, I would say it's very similar to k-means, but it's taking it one step further. So sometimes data is structured so that there's not really just 3 or 4 different groups of data, that is clusters. Sometimes it is structured so that there are subclasses, that is subclusters within the data. So if you take a look at this data and you said, okay, I'm going to pick k equals 2, then you'd probably come up with something like this. These are the data points that are close together, and those form the k equals 2 clusters. But and if I picked but the problem is that, I can split up the data as cluster 1, cluster 2 here. But really, if I take a look further, I can split up cluster 2 into 2 more clusters. And it's not so much that I find that this cluster is wrong. It's just that there seems to be additional structure within cluster 2 that doesn't seem to occur in cluster 1. So I might say, okay, the way that these data cluster is that there is one big cluster on the left side there, but then there's also this other cluster which breaks down into 2 more subclusters. And that's the basis of hierarchical clustering, is that you can take the same idea, clustering, but you can make a hierarchy out of those clusters. Okay, so agglomerative of hierarchical clustering builds up clusters from the base, and then builds a dendrogram out of that to correspond to the similarity of the children. So I'm just going to give you a little example about how our agglomerative hierarchical clustering works and builds up those clusters, and I think you'll get a sense of what hierarchical clustering is doing as well. Okay, so to start off with, imagine that you have these 4 data points along the x1 and x2 axis. And the whole idea is to build up a little a hierarchy of how these things are clustered together. So if just right away we can see that, these 2 cluster together and these 2 cluster together, and probably there's not much relationship between the 2. So and that's kind of how this works, is that first you start off with every data point in its own cluster. So and then from there, you build it up into one big cluster. That's why they call it agglomerative hierarchical clustering. They're just gluing them together. Okay, so the first part of the algorithm is to find which is the shortest distance between these points. So I look around, and the shortest distance between all these points is between these 2 points right here. Okay, so now I say I'm going to put these into their own cluster. So What does that mean? Is I'm gonna draw out this tree over here. I'm gonna join them together with this sort of upside down U. Now I'll show you. It'll become clear why I'm drawing it in this way when I do the second one. So the next step is like, okay, I'm gonna try to find the next similar points, and then most similar points. It turns out to be these 2 points. And so now I say, okay, I'm gonna draw another upside down U here that indicates that these 2 points are now in the same cluster. And you might notice that I drew them a little bit higher, and that's because its cluster, like this cluster, has children that are a little bit less similar to each other. So this cluster is a little bit tighter than this cluster, so this cluster I draw a little bit higher. Then I say, okay, out of these clusters that are remaining, which clusters are the closest together? Well, since I only have 2 clusters left, then the closest clusters are really the only possible ones, which is the last remaining. So I say, okay, I'm going to draw a connection between these 2 clusters, and then draw a upside down U between those 2. So now the algorithm is finished. I have built up a hierarchy of how these clusters break down, starting from all the data into separate little clusters. So what's neat about this is that this tree is called a dendrogram, and it comes from the Greek term, just dendron, tree, and then gram, I guess, meaning mathematical figure. But it's neat because not only does it tell you which things group together, but also how well they group together. So you can say, well, these are pretty tight, these ones are pretty loose, without actually looking at the data, but and they don't really go together that well. You know, they're pretty far apart, relatively speaking. So this is the basis of all agglomerative hierarchical clustering, and you can kind of think of it as more, I guess, advanced k-means, because with k-means you really have to pick. First of all, you have to pick 1k number of clusters, but here you can explore that in a little bit more detail. So if you have a large number of data points here, you can see how instead of picking 1k, you can say, well, I'm not really interested in this cluster, so I'm not going to look down on the tree any further. But for this cluster, I think I wanted to get into it a little bit further, and I think that might become a little clearer in the example I'll give at the end of the section. Okay, so divisive hierarchical clustering is not really used as much, so there's not as much research into this method. Agglomerative clustering needs to measure the distance between clusters, so you have to find, and I sort of glossed over that in describing the algorithm, but it does make a difference how you measure. So these are 3 different ways of measuring the distance between clusters and the different dendrograms that would come out with the same data. Single linkage, what it does is it just says, okay, I'm going to take a look at, if I'm going to measure the distance between 2 clusters, I'll find the closest distance between points. Seems the most obvious way to do it. The problem is that it tends to lead to chaining. So that means like you tend to pull in points one at a time, and you can see this by the way the dendrogram looks. It sort of adds on 1 point and 1 point and 1 point at a time rather than joining together bigger clusters. And that effect is fairly well known. Complete linkage uses the furthest distance away between the 2 points. And so that seems like it would solve the problem, but then it leads to another problem where, you know, outliers still have a huge effect on clustering. And when you look at what the clusters look like, especially in the 2-dimensional plane, it seems like they don't obey what a human would select in terms of like which clusters belong together. Anyways, it's a little tricky to understand how that would work, and this diagram is from the Elements of Statistical Learning, chapter 14, and I recommend going through it. The mean linkage, which seems like it would be the obvious compromise between single linkage and complete linkage, it does nicely remove some of the problems of both of them. But now suddenly you've made your distance technique dependent on scale. So the average distance between the two, if you just logged your data, you would end up with a different dendrogram. Just to give you an idea of what these terms mean, because we'll be using them in the session on Thursday, and they can have an effect on your dendrograms. Okay, I wanted to go through a little bit of a example here on opioid prescribing that came from some of our own research, and it was, I think it's helpful in understanding a much more practical problem of using this in science. Again, not to try to answer some question directly, but to give us hypotheses that we could test later using more traditional statistical techniques. So if you probably seen it on the news lately, but opioid prescribing is a huge issue in North America, in Canada, and the United States. And opioid prescribing has been on the increase as well. It's not all of the opioid problems that are being described in the news are due to prescription opioids, but at least there is some relationship between the rise in opioid prescriptions and opioid overdose death. In any case, what we were interested in our study was to understand what do physicians prescribe to somebody as a first opioid. That is, for somebody who has never received opioids in the past 3 or 4 years, and what do doctors tend to prescribe first? And there are guidelines on this kind of thing. Like codeine is a relatively weaker opioid than hydromorphone oxycodone, especially fentanyl. But doctors have very different prescribing behaviors. So we had the healthcare insurance database in Quebec, and we could tell what doctors were prescribing, at least to those who were insured by the provincial insurer. So if you take a look at this example of 4 doctors, what they prescribed, what was the probability they would prescribe one of these 5 classes of opioids? Doctor 1 looks pretty similar to Doctor 4. So I've sort of colored these boxes in darker blue if this number is higher, and a much lighter blue going to white if it's 0 for the percentage. So, and that's important because in the next slide I'll be doing this for many doctors. So if you look at 4 doctors, it's pretty obvious that 1 and 4 are pretty similar, and maybe 2 and 3 belong in their own little cluster together. Unfortunately, fortunately, we were able to study thousands and thousands of doctors, but it was harder for us to get a handle on different patterns in their prescribing. So now I'm going to show you this sort of same bars, except for at least 1,000 doctors. Okay. So looking at this opioid prescribing examples, now each doctor of the 1,000 doctors is represented by a very thin blue line. And for each of the classes of opioids, their color is very dark if they prescribe that particular opioid a lot. So in the very top line, this doctor prescribed a lot of morphine, some hydromorphone, and not a lot of this codeine and fentanyl. So what we were able to do here is pick out some very interesting patterns in the data. On the left-hand side, what it shows is the dendrogram fit by agglomerative clustering, exactly as I was describing it. So the distance metric was the Euclidean distance between these 5 numbers, the percentages of opioid prescription for each. And then I fit in an agglomerative hierarchical clustering to that. I colored in some of these, some sections of these data, but that's entirely of my own choosing. The algorithm itself did not select these colors, but I wanted to highlight them because by eye, I could see that these were the groups sort of created by the data. So basically, what we found out here is that physicians kind of prescribe one opioid regardless. So it's not that they're really distinguishing one patient from the other. When a patient has never received opioids before, a large group of physicians will just prescribe hydromorphone. And another group of physicians will just prescribe oxycodone and pretty much nothing else, which is particularly interesting because there's not that much difference between oxycodone and hydromorphone. In the doses that they're prescribed at, it's not clear what the advantages of one over the other would be. However, codeine, you could see it would be a little bit easier to understand because it's a less powerful opioid, and maybe for fentanyl because it's a much more powerful opioid. But the differences between these three, hydromorphone, morphine, and oxycodone, were certainly not expected to be have such a strong preference. So it's clear that physicians have a preference for one kind of drug, and they kind of just stick to it regardless of what happens. And it was interesting to see actually how this changes over time. So again, the purpose of this was not to say, okay, I'm going to publish this picture right away and show that and make those claims that I just made now. But the purpose was to generate hypotheses, like people just tend to stick with hydromorphone regardless of what patient they see. That kind of thing is a hypothesis that we have generated using unsupervised learning that we can test with some other appropriate statistical methods. Okay, I'm going to move to principal components analysis. This technique is a little bit different from k-means and hierarchical clustering, but it's quite interesting as well, and it's originally not a machine learning technique. It was originally a statistical technique, but it's quite clear now that it's been sort of brought into the unsupervised learning fold. Okay, so principal components analysis is really very heavy in terms of linear algebra. So I didn't think it would be a great idea to try to go through that math with you in like 10 minutes. But I did want to give you a sense of what the principal component analysis is used for, and perhaps spark a little bit of interest in how the math works in the background. It is described fairly well in the elements of statistical learning in chapter 14. This figure here is actually from the elements of statistical learning as well. So the idea of principal components analysis is that instead of saying, I'm going to provide you with which cluster this belongs to, like a group where all the points in this little group are very similar to each other, it kind of reduces the data to a smaller number of variables. So you can start with 10 variables and say, you know what, actually these 5 variables are very correlated with each other. These 5 variables are very correlated to each other. There's basically only 2 components to this data. You know, so if you have like height and weight, two things that are extremely correlated with each other. And let's imagine that this is this horizontal axis could be height, and this would be weight. Now they're correlated. It's not perfect, right? So you can see that if the little red dots here are the data points, there's a straight line going up. Now, what principal components does is provide the essential structure of the data. It says, well, you know what? You could probably just come up with one variable that is representative of both height and weight at the same time by sort of drawing a line through these points and saying, you know, that we can approximate this data, these 2 variables, with just one straight line. That is, so you can, and intuitively you can imagine them doing this by using something like BMI. That isn't exactly what it's doing. It's not just dividing one by the other, but you can sort of in your head imagine how two variables can be through a functional form sort of combined into one a data point. And so like BMI, you do lose some information. So BMI, you no longer can capture exactly what their height or their weight was, and but you do get one measure that might be valuable to you in your in further analysis. So instead of finding out what is the what cluster something belongs to, you say, actually my data only has a few important components, a few points. All these variables can be summarized down into a few essential components. So I'm going to give you a few examples of that. I think it's easiest to understand with some pictures. So if you imagined, and they do this in the elements of statistical learning, you had a data set that was in 3 dimensions. So you had 3 variables, and they're trying to show you those 3 variables here, and they're all sort of around this half sphere in the data set. So this is just this sort of structure of the data, that they're all sort of sitting on this surface. Now, what principal components analysis would do is say, you know what, even if I take these 3 dimensions of data, I can kind of just take the plane here. So I can take a hyperplane, or well, actually just a 2-dimensional plane, and I can approximate that by projecting, and then project this 3-dimensional data into 2-dimensional data here. So this is a rank 2 linear approximation to that data. And the reason why this works is because the principal components analysis has sort of detected that there is no data in certain points. Like the data couldn't fall too far inside this circle. It couldn't be too far off the surface either. And so there was a strong correlation between where you were on the Z plane and where you were on the X and Y. So you can sort of, you can exactly flatten it out and not lose very much information. You do lose some information, right? So just like with, and people who work a lot in the environment might understand, and geography might be familiar with this kind of thing. You know, when you take the surface of the Earth and you want to make a map out of it, you're projecting it down onto the 2-dimensional plane, you do lose some accuracy. So the distances between the points might be warped a little bit, but it kind of helps you understand that it simplifies the structure of your data. Now to sort of see this in another light, I'm going to take a look at the NIST example of principal components analysis, also found in the elements of statistical learning. So they took a bunch of 3s that were handwritten, and they ran principal components analysis on it. And I wanted to show you exactly what the principal components, the first 2 principal components, looks like in terms of a few examples. So they took each of these green dots represents one of these 3s, and so then they plotted them in terms of each of their principal components, and then picked out these sampled points, the actual 3s that were represented by these green dots. So the first, if you look at this grid of 3s, there's a sort of obvious pattern to it. So as you move from left to right, the 3s get a little bit more, wider. So these 3s are drawn, sort of in this space, but as you move to the right, the 3s almost touch the edges of the little box. So they're a little bit wider. And as you move from the top to the bottom, the thickness of the line gets a lot thicker. So these are thin lines, and these are thick lines at the bottom. And to me, this is kind of amazing. Like the algorithm is not given any knowledge about handwriting in general, but what it's done is it's picked out sort of the principal components, the essential characteristics of these data. Now, what it was fed was each of these little pixels of these 3s was fed in as its own variable, and it picked out that there's a ton of correlation here, and that there's essentially all these 3s can be described in 2 different ways. One is their width, and the other is their thickness. So kind of an amazing that it could pick this out this easily. So this is it's a little bit trickier to understand how you would break this down, but you can imagine that this would be very nice used in conjunction with a supervised learning algorithm. So you might pre-process your data with an unsupervised learning and then feed it into supervised learning and just saying, okay, to the supervised learning algorithm, okay, here's the thickness or the thinness of the three. Okay, so now for a summary. So unsupervised learning really is all about finding structure in your data. It's not about predicting something, and that's a little bit hard to wrap your head around but what it really it shares a lot of common elements with is visualization. So you don't always know what you're looking for before you start. Like with the opioids example, we didn't know that physicians had such a strong preference for certain opioids. But and we didn't know it even after we visualized it, but we had that idea. We ended up with that hypothesis afterwards, and we could test it rigorously. And I think that's what makes them such powerful tools, is that you can just, if you're having trouble understanding something, or if you're having trouble, like, where to start with a new data set that you're given to analyze, this can really it could generate the hypotheses that you need to start just testing rigorously. So I think these are simple, powerful tools. I think either they're underused, they're not often reported in scientific research, and that's because people aren't often interested in just hearing about the hypotheses you have. They want to hear about what you've tested. So I think that they may be more used than they are reported, but they certainly have been helpful in my own research, and I hope I've given you enough information to spark an interest in this field. A last slide I have here is some additional reading that you might do. The Elements of Statistical Learning is quite good, chapter 14. And Mackay's, like I was saying before, especially for k-means, chapter 20 is excellent. I find him an excellent author. And chapter 34, an independent component analysis, not quite the same as principal component analysis, but an interesting unsupervised learning technique as well. Thank you very much.
Thanks, Aman, for the great presentation today. We do have a question. In your experience or knowledge, have you found any difference in the performance of model accuracy when comparing feature selection based on random forest feature importance or PCA?
I mean, I haven't done a head-to-head comparison myself of those two algorithms, but feature selection is really important, and you can get a sense of it when you think about exactly what the computer is doing. So imagine you instead of if you had a set of textual data and you were trying to use random forest to pick out something like, oh, I was going to identify the diagnosis of some illness within some text data, and you fed it the words and it had some accuracy. Now imagine that instead of just feeding it the words, you fed it the letters. So something that's a little bit further down, a little bit more fine, but it's essentially the same data, just not at a different level of granularity. It really is. It's going to matter because what the feature selection allows you to do is allows you to give the algorithm a little bit of a boost and understand, use your scientific knowledge to aid at what level this algorithm is going to work best. Maybe that's not your exact. It doesn't answer your question exactly, but I haven't compared those two things directly. So no, I don't know the precise answer to that, but there aren't going to be huge differences between different specific feature selection algorithms.